have been looking at deriving expressions for inductances in electrical machines, and in the last lecture we had tried to derive an expression for the mutual inductance between the rotor coil and the stator coil for the case where the stator is a cylindrical structure, but the rotor is a salient pole structure. And in order to derive the inductance, the procedure we had adopted was, first we excite the rotor coil. When you excite the rotor coil, there is a certain MMF, and because of that flux is generated inside the machine. And we had seen over the last couple of classes what happens to that flux waveform or the flux generated inside the machine as the rotor begins to rotate. We see that as the rotor rotates, the flux density waveform travels along with the rotor. There is a certain flux density distribution inside the machine. That means as you travel around the inner circumference of the stator, you encounter flux densities at various points, and that then is called as a flux density distribution around the air gap or around the circumference of the stator, inner circumference of the stator. And when the rotor rotates, this flux density distribution also rotates along with it, because the source of that excitation is from the stator. So we have excited the rotor coil. We had then found out the flux density distribution we had found out the flux density distribution around the inner circumference of the stator, and then this waveform was a quasi square wave, in the sense it has a flat top over a certain angular distance, and then it is 0 elsewhere, and then a negative flat top, and so on. In order to deal with this waveform, we resolved this waveform, resolved B of alpha into Fourier series, thereby you have an analytical expression in terms of alpha. And then now that you know the distribution of flux density around the circumference of the stator, you then formulate an expression for flux linkage In order to do this, we considered first an elemental flux linkage, which means we looked at an elemental area around the inner circumference of the stator. We found out how much flux was passing through that. We know the expression for flux density, and flux density multiplied by the area is then the flux passing through that elemental area. multiplied by the number of turns is then the flux linkage, and then we integrated this flux linkage expression, integrate this flux linkage expression over the span of the coil, over area spanned by the coil on stator coil span, and then you derive the expression for flux linkage, and we saw that this flux linkage has various terms relating to the fundamental and the third harmonic and the fifth harmonic and so on. And then we observed that these terms pertaining to the harmonics die down fairly rapidly, and for most analysis it is sufficient to consider only the fundamental term, and that fundamental term we found in the last lecture could be written as psi s is equal to this expression. So let us write down this once again. It is minus 8 b hat ns L into r by pi cos gamma into cos theta r. So what we have is psi s is equal to minus 8 b hat ns L into r by pi into cos gamma into cos theta r. This is the flux linkage. Now we know that B hat is the peak flux density. How to find out the peak flux density? If we look at the rotor geometry which we saw in the last class, I am scrolling back. This is the geometry that we have been considering. In this geometry, what is happening is that the flux lines would travel along the rotor and then go into the stator and then come around and complete the flux loop in this manner. We have also noticed that in the air gap areas there is bound to be very little flux. Majority of the flux is going to go through the pole faces. We had earlier seen a flux density distribution that is there in this system. We saw how the flux lines go. So these flux lines are going to go mainly here, and we have also seen that the MMF or the value of H that is dropped, that is there along this flux path, is predominantly concentrated in the air gaps, and we had derived an expression for that. Therefore what we can say is if you apply Ampere's law around that loop of flux, then what we have is H at the air gap multiplied by the air gap length. This is along one air gap of one pole face, and then you have similarly another pole face air gap. So 2 times this must be equal to the number of turns in the rotor multiplied by I in the rotor, and therefore from this what we have is Hg equals Nr into Ir by 2 times Lg, and this is in the air gap, and therefore we know that this is equal to B hat divided by, or B divided by mu naught, and therefore the expression you have is B hat equals mu naught Nr into Ir divided by 2 times Lg. So that is the expression you have. So this can now be substituted into the expression for the flux linkage. So you have psi s equals minus 8 B hat Ns, instead of B hat we are going to substitute the new expression, Therefore, that is mu naught n r into I r divided by 2 times L g multiplied by n s into L into r multiplied by cos gamma into cos theta r, and therefore one can now write this as psi s divided by I r is minus 8 mu naught n s n r into L into r into cos gamma divided by 2 times L g into cos theta r, which is then minus a maximum value of the mutual inductance between the stator and rotor multiplied by cos of theta r. So, this is then the mutual inductance between the stator and the rotor. We are considering only the fundamental component of that. So, we find that it changes as cosine of the angle. Which finally leads to this value of mutual inductance equals MSR hat, maybe a minus sign, and then cos of theta r. So, we have derived then an expression for the variation of mutual inductance as the rotor changes its angle. Now, in this system we have one coil on the stator, one coil on the rotor, which means electrically when we try to write down expressions for describing the system behavior, we would have to find out the self inductance of this coil, we have to find out the self inductance of this coil, and then there is a mutual inductance between these two. So, these are the three inductances that we would encounter, and what we have done now is we have derived an expression for the mutual inductance between the two coils. We know how to derive an expression for the self inductance, that is straightforward. We have done that earlier for the cylindrical rotor case. For the cylindrical stator case also it is very simple. You have the, if you take the machine and then you have a rotor which is there. Now, if the rotor is excited and the rotor were going to rotate, the flux generated by the rotor would be independent of where the rotor is. It always sees a constant air gap along this region, and we already know that there is not much of flux that is available in the air gaps, and therefore we can easily say that the flux that is thereby generated is given by the MMF, which is NR into IR, that is the MMF, divided by the total reluctance, and the reluctance is given by the reluctance of air gap 1 plus reluctance of air gap 2, air gap 1 being under pole phase say 1 and reluctance 2 being the air gap under pole phase 2. So, if you add these two up, you get the total reluctance. Each reluctance is then described by length of the air gap divided by mu naught into area of the air gap. And since this is equal on both sides, the total reluctance is then 2 times this value, and therefore you can write the flux that is produced as NR into IR divided by 2 times length of the air gap multiplied by mu naught into area of the air gap, and the flux linkage is nothing but N R into phi, because we are considering now the self inductance of the rotor, it is N R into phi, which means N R square multiplied by I R into mu naught into A g by 2 times L g, which means that the self inductance L R is nothing but psi, let us call this psi r by I R, which is N R square multiplied by mu naught A g divided by 2 times L g, and therefore we know the self inductance of the rotor coil. So we have derived mutual inductance, we have derived self inductance of the rotor. Now we need to derive an expression for the self inductance of the stator coil. So in order to derive an expression for the self inductance of the stator coil, we need to excite the stator coil. So the procedure will be very similar to what we had done earlier. Now excite the stator coil, and then find flux linkage in stator, and then flux linkage per unit ampere is your self inductance. Now the question is, how do we find out the flux linkage? In the earlier approach, what we did was, in order to find out the flux linkage, we found out the flux density distribution around the stator and then resolved it into Fourier series, found out the flux passing through an elemental area, and then did an integration. Now in this case, and the whole method was based on our observation of how the flux density distribution in the machine is going to appear as you rotate the rotor. We had started from there. Now let us see what will happen if you excite the stator and the rotor begins to move. So here you have some pictures of how the flux density flux lines are going to look like in the case of a salient pole rotor and a cylindrical stator. You can see that the stator is cylindrical, this is your cylindrical stator, and here you have the salient pole rotor. So with the rotor located at this particular angle, and if you excite the stator coils are here, if you excite the stator coils, then the flux lines can be seen to be like this. You can see that flux lines concentrate around the stator coil here and here. It is also evident that there are plenty of flux lines here, there is very little flux lines sparsely distributed over here. So one can infer that the flux density in these regions would be high, flux density in these regions would be high, flux density in all these areas would be low. It would decrease as you travel from here. This region would have a very low flux density, and the flux density again increases as you travel to this area. In this area you can see that there is very little flux. So here again there is a dip in flux density, and then flux density again rises and then falls down. This is the situation for the rotor like this. Now let the rotor move. So you come to the next position, the rotor has rotated a little anti-clockwise, and you see that again under the pole face there is a rather high flux density distribution, but now it is occurring in this part of the pole face. Below the slot it is a lower flux density, and here the flux density is low and it picks up as you come here. The flux density here is high, here it is high, and as you go around it gradually falls, this region would have a very low flux density. Let the rotate a little more. Again you have a rather high flux density region here, and then the flux density region falls and you have low flux density and high flux density regions here. Rotor rotates a little more. Now you have high flux density regions again near around the rotor area, whereas these areas now have very little flux density. This again high flux density, here low flux density. Rotor rotates a little more. You can see that the high flux density areas seem to be traveling along with the rotor. Now the flux density areas, I mean in areas that are in other zones, these are all small. The rotor rotates a little more. Again you can see that this higher flux density area is traveling along with the rotor. In these areas flux density is pretty small. One more rotation, so here it is. So we have seen at different angles how the flux lines look like. It appears as if the machine always looks at the entire air gap area. There is this, all this region is air, all here is air. Air gap here is small, whereas air gap here is large, and one can see that the machine appears to look at it as if, you see, you are exciting the stator and you want to find out the flux that is thereby developed, and always wherever this air gap is low the flux levels developed are high, and wherever this air gap is high the flux levels developed are low, and the region where air gap is high or air gap is low will depend upon where the rotor is. If the rotor is at this angle as is shown here, this region of the stator circumference has low air gap, and as the rotor moves this region of the stator circumference now becomes one with a high air gap. So where the air gap is low, flux levels seem to be high, and it is very difficult to predict how this flux density distribution is going to change, what will be the wave shape of this flux density distribution. Unlike in the case where the rotor was excited and the rotor was moving, it is true that the flux density in the pole phase was always high and that region moved along with the rotor, but now the situation is slightly different. Even within the phase of the rotor the flux density distribution can change. For example, now you see that in the middle of the rotor pole phase the flux density level is low, whereas on these two sides it is high. It is high, but since flux is passing out from this side and entering back into this side, the flux density levels here, if they are greater than 0 at some high value, the flux density levels here will be less than 0 at some high value. Whereas now as the rotor rotates, even under the pole phase you see that the flux density distributions are going to change. So one can sort of say that the machine is looking at what is happening inside as if there are two different air gaps that are available. One air gap that is related to what is happening in the small air gap area, another air gap which is giving a response or flux generation which is related to what is happening in the large air gap area. And therefore in order to analyze how this system is going to behave, what is normally done is that you have the stator of the machine which is cylindrical, and you have the rotor of the machine which is salient pole, as you travel around the inner circumference of the stator, the air gap length dramatically changes. In as you approach the pole faces, the air gap is small. As you move away from the pole faces, air gap is large, and that is the kind of varying air gap that is seen by the stator coil. And therefore, in order to analyze this kind of a system, what is done is that you assume that the machine or the coil on the stator, assume that the coil on the stator sees a geometry with two air gaps. That is, it appears to the stator as if there is one rotor which is always moving, one cylindrical rotor which is always moving, such that the air gap is small. Why it is so? We have seen in the pictures here that there is, irrespective of where the rotor is, there is always a region nearby the rotor which has high flux densities. So, these regions always behave as if the air gap is small, and this region moves as the rotor rotates. And there are certain regions where the air gap flux density is always low, and that region also moves as the rotor rotates. And therefore, we then say that the stator winding looks always at one air gap that is small and another cylindrical rotor which has an air gap which is large. So, let us call the small air gap as GD, and let us call this large air gap as GQ, which means that we are saying that there are hypothetically two rotors in the machine, both of which are cylindrical. Now, this has an effective air gap which is GD, and then there is another rotor inside the machine which is also cylindrical and has another air gap GQ. Now, the net response of the flux is the response produced due to both these rotors having an air gap GD and GQ. How much of flux is going to act along the air gap GD, how much of MMF is going to act along the air gap GD, and how much along GQ is what we have to now determine. For that, what we do is, how we ultimately, of course, one has to see, if we do all this, whether the estimate of the inductance of the stator is similar to what we are actually observing. If it is similar to what we are observing, then perhaps we can say our assumptions and procedure is all right. Now that we are looking at a stator that is cylindrical and having considered the rotor as effectively being composed of two cylindrical rotor structures, in order to find out what the MMF is, we will have to now consider what happens with the cylindrical rotor structure. And therefore, if we now look at the, here is your stator and here is the rotor, assume that they are nice circles. Now, you have a coil here and a coil here in a slot. In the earlier case, to find out the mutual inductance, we started with the flux density distribution. Similarly, here we can think of an MMF distribution to start with. It is more convenient to start with an MMF distribution. How to find out the MMF distribution? If you have a cylindrical stator and a cylindrical rotor like this, you will find flux lines that are going to cross like this and come around. Similarly here, and one can now write the expression for Ampere's law around one of these loops. If you go around any one of these loops, then you will have Hg into Lg. Let us say we are looking at the d axis MMF. So Lgd, this would then be Lgd, or if we look at the actual MMF itself, let us look at it that way, Hg into Lg, and 2 times there is one Hg into Lg dropping here, another Hg into Lg here. This is equal to Nr Ns into Is, and therefore Hg into Lg is equal to Ns into Is by 2. We can therefore get Hg as Ns into Is by 2 Lg. This would give you Hg. The H into L itself is then the MMF that is dropped across one air gap. Here you have a similar MMF that is dropped across the other air gap. Here flux lines, let us say, are travelling into the rotor, whereas here flux lines are travelling away from the rotor. So if you call one MMF as positive, the other MMF is obviously negative, because it is now causing flux to flow outside. This is causing flux to flow inside. So if you draw this at any angle along the circumference of the stator or the rotor, any loop that you take will always give the same equation. For example, let us say you take another loop here, it would still give the same expression, the same Hg into Lg. At this point we have said that the flux travels normal, so Hg into Lg, and then again Hg into Lg in absolute terms should be equal to that. So what we have is, if you now plot the actual MMF variation around the circumference that is there, this is your angle alpha as you travel around the circumference, and this is let us say MMF. This MMF is constant at a value equal to Ns into Is by 2 as you move around alpha. So what you would have is, from alpha equal to 0 to alpha equal to that, if you call that as 1 sine, well, we have called, let us take it this way, that would be your MMF distribution, each of magnitude Ns Is by 2. If that is Ns Is by 2, here it will be minus Ns Is by 2. It depends on what is the convention you choose. If you choose to call flux lines going from rotor to stator as positive, then flux lines going from stator to rotor will be negative. If you call flux lines going from rotor to stator as negative, then flux lines going from stator to rotor will be plus. So, one of these conventions, if we draw it this way, it is NSIS by 2 and minus NSIS by 2, this is the flux density distribution. So, I mean this is the MMF distribution. So, what we see is that if the rotor structure is cylindrical, one can write down the way MMF changes as you travel around the circumference of the air gap. And what we have seen earlier in the expressions for the rotor mutual inductance, rotor to stator mutual inductance, we have been saying that it is sufficient to consider the fundamental component alone. So, let us do that here also. We will take the fundamental component of this MMF. The fundamental component of this MMF waveform is going to look like this. And it is an easy matter to find out the amplitude of the fundamental component. You have to resolve the square wave into its Fourier series and look at the amplitude of the fundamental component, and that is a very standard exercise which I would leave it to you to do the expansion of the Fourier series and to find then that the amplitude of the fundamental, let us call that as f hat. The amplitude of the fundamental is given by 4 by pi into ns is by 2. This is the amplitude of the fundamental component of the MMF distribution around the circumference of the stator, and therefore one can find right now MMF distribution as a function of alpha. That means as you travel around this circumference, what is the expression for the MMF? That is nothing but f hat into sine of alpha. So, that means that at alpha equal to 0 f is 0, as alpha becomes pi by 2 it reaches the maximum value of f hat, and then so on. It is a sinusoidal distribution. Now, this is the distribution that is there along the circumference, inner circumference of the stator, but this MMF now acts along two air gaps that we have now called the air gap lengths, we have called as LGD and LGQ, GD and GQ. And how much of this MMF acts along those two air gaps? We have seen that as the rotor is going to rotate, the flux levels move along with the rotor, and one part of this MMF then acts along the low air gap area, another part acts along the high air gap area as the rotor moves. So, we then say that you resolve this so if you have the stator geometry, stator, and then let us say you have the rotor like this, the MMF distribution that we have written is an MMF that varies from, here is your alpha equal to 0 and then you travel along, at alpha equal to 90 degrees you reach the maximum value of MMF, alpha equal to 90 degrees is the maximum MMF, and then as you go along you reach alpha equal to 180 degrees, you get the minimum value of MMF, and so on. Now the maximum value of MMF occurs at alpha equal to 90 degrees. In order to find out how much of this MMF acts along the rotor which has a small air gap area and that part which has a large air gap length, we resolve this MMF into two parts, one which is always acting along the rotor axis, that means one which always acts along this axis, and another which always acts along this axis. Now if we do that, then this MMF will always see a small air gap and this part of the MMF will always see a large air gap. That is in essence why we decided to have two air gaps that are acting in the machine, that seem to be acting in the machine. So this axis let us call as the D axis, this axis let us call as the Q axis. The word D generally stands for direct axis, direct referring to the axis of the rotor pole of the pole structure, and Q standing for quadrature. Axis. So how does one resolve this into these two parts? Now the MMF itself, the stator generated MMF, we see that it has a maximum value on this axis, maximum value in the sense it reaches the absolute value of the MMF is maximum along this axis. You can see that the MMF reaches a maximum at alpha equal to 90 degrees and again it reaches a maximum at alpha equal to 270 degrees. So that means at this position. So MMF is maximum either here or here, and the location where the MMF is maximum, we use that to define the axis of that MMF. So this line is defined as the axis of the stator MMF, and that place where the maximum amplitude, instantaneous amplitude occurs greater than 0, this is the reference axis, is chosen as a reference axis in order to define the rotor angle, that is your theta r. Now we say therefore that the rotor is at an angle 0 if this rotor bar were horizontal, and we say that the rotor angle is equal to 90 degrees if the rotor bar were arranged in this manner. So that is then the rotor angle. If this is the rotor angle, then by geometry what one can see is that this angle is also the rotor angle, because these two axes are oriented 90 degrees to each other. So with this then what we want to do is to try and resolve this MMF, stator MMF, along these two axes. So in order to do that, if the maximum value occurring here is f hat, then f d, which is the resolved value of the stator MMF acting along the d axis, is given by f hat, that is the peak f d hat, f hat into cos of theta r. F hat is the maximum value of the stator MMF acting along this axis. You want to consider the component of that along the d axis. So that is f hat into cos theta r is that value, and the component acting along q axis is f hat into sin theta r, this acting along q axis. So, we have now arrived at expressions for denoting the peak value of the MMFs acting along the d and q axis. We now have to define the spatial distribution of this. You see that the MMF generated by the stator is spatially distributed, that means as you travel around space, what is the variation of MMF that you would encounter? That was given by this expression f hat into sin alpha. Now, by resolving these two expressions describe the peak, and therefore, what would the spatial distribution be? F d as a function of alpha will then be this peak value f d hat multiplied by cos of alpha minus pi by 2 plus theta r. This would then describe the variation of that f d MMF in a sinusoidal fashion about that. F q of alpha will then be f q hat multiplied by cos of alpha minus theta r. So, we can write this as f d of alpha equals f d hat multiplied by cos of alpha minus pi by 2 minus theta r, which is f d hat multiplied by cos of alpha minus theta r minus pi by 2, which is f d hat multiplied by cos of pi by 2 minus alpha plus theta r, which is equal to f d hat multiplied by, this is cos of 90 minus theta. So, I can call this as minus of alpha minus theta r minus of alpha minus theta r, and therefore, this is f d hat into sin of alpha minus theta r. And then what you have is f q alpha is f q hat into cos of alpha minus theta r. So, these are two expressions for the spatial variation of f d and f q. Now, these MMFs are now going to act along their respective air gaps. F d acts along the smaller air gap saying L g d, and f q acts along the larger air gap L g q. The net flux at any given angle will be the flux caused by the d axis MMF and this q axis MMF. We need to find out the flux linkage of the stator winding with the fluxes produced by these two, and then as usual do the process of integration in order to find the total flux linkage, and then flux linkage divided by unit current is going to give us the total inductance. So, these steps we will see in the next lecture to come. We will stop at this point.